Now as I return to the Residence Inn Marriot, Los Angeles, California, room 709, and we're on the amazing 5x12 matrix and the PDM process. But specifically now, we are on sort of a relatively new topic, which is the magnetization property or affinity-like property of the amazing 5x12 matrix. Yours truly, Dolphy Gilpin, is here with you again. And since we have sort of described what this affinity-like process is in previous video production, let us just jump straight into the continuity of it here. And so we have spotted this matrix in our research, and the amazing 5x12 matrix, because of its many luminous, astronomical, exponential production of matrices that are of higher dimensions and of lower dimension than this one, it sort of attracts itself to the interest thereof. And so what we have here now is epsilon 1, epsilon 2, epsilon 3 to epsilon 6. And these matrices were spotted in aeronautic and astronautic in Unit 5 engineering. And giving credit to where credit is due, it was spotted by this from Professor, he has a initial of PAL, P-A-L, which is Paul A. Lagaze, Professor of Aeronautic and Astronautic Engineering. So I spotted the matrix, and because of the magnetization property of the amazing 5x12 matrix, which was of interest, I expounded and enhanced the procedure. And so this is now, we'll have to do, those of you who are not familiar, some background reading on this. I have to explain the epsilon 1 and the E1s and the B12 and the sigmas and the nu and the G's. Anyhow, here we have with that, and it's a 6x6 square here, and this is 1 over E2 in continuity here, minus V23 over E2 and 0, 0, 0. I mean, these terms with sigmas and e's are 0. And we have now minus V31 over E3 minus V32 over E3, 1 over E3, 0, 0, 0. And the rest of them here, 4 will be 0, 0, 0, 0, 0, 0 for these terms, all zeros. 1 over G23, 0, 0, 0, 1 over G13, 0, 0, 0, 1 over G12. And this is now sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and sigma 6. And we call this now the compliance matrix, or the orthotropic case. No, this is for the orthotropic case. For the isotropic case, as we noted in the last one, we get the material which is less elastic, constant, which is less than n, and the orthotropic material, we no longer have any more zero terms in the elasticity or compliance matrix, which is this. but more non-zero terms are related. And for the isotropic case now, what is established is that all extensional moduli are the same. So that now E1 equals E2. E1, the E's are the extensional modulus, equals E3 equals E. This is for the isotropic case, for the material. And for all the Poisson ratios, they are the same. And for the Poisson ratio, we have now that V12 equals V21 equals V13 equals V31 equals V23 equals V32 equals. This could be V or the Greek letter V. And all shear moduli are the same. This is for the isotropic case. All shear moduli are the same. And we have now that G4 equals G5 equals G6 equals G. And this is for the isotropic case, in which the extensional moduli are the same, Poisson ratio are the same, and the shear moduli G4, G5, G6 equal G are the same. So let us see now the matrix form of these isotropic case, the orthotropic case, and the anisotropic case. We continue at the Residence Inn Marriot in Los Angeles, California, 5933 West Central Boulevard, room 709, with our amazing 5x5 matrix and its magnetization or affinity-like properties. It attracts itself toward the matrices operation and seeks relations and analysis wherever the interest occurs. This we call described as the magnetization property of the amazing 5x12 matrix. I noticed that we could have worked from the linear equation into the matrix, but because of the astronomical or exponential amount of matrix produced by our process, it has an attractive power, and it attracts or magnetizes all the matrices and incorporate or integrate them into the operation. And so we move now from the matrices to the linear equation, which has a similar form. And this is in the engineering stress strain equation. So what we have now is that epsilon 1 equals to 1 over E1, and you will see exactly how the matrices are sigma 1 minus V12 sigma 2 minus V13 sigma 3 minus 1 4 sigma 4 minus 1 5 sigma 5 minus 1 6 sigma 6. That's for epsilon 1. For epsilon 2, we have 1 over E2, Leroy's equation, V21 sigma 1 plus sigma 2 minus V23 sigma 3 minus U23 sigma 3 minus U24 sigma 4 minus U25 sigma 5 minus U26 sigma 6. Epsilon 3 is equal now to 1 over E3 minus V31 sigma 1 minus V32 2 plus sigma 3 minus n 3 4 3 4 3 5 sigma 5 gamma equals to epsilon 4 equals to 1 over G4 into 4 1 sigma 1 gamma equals epsilon 5 for 1 over G5 gamma 6 equals epsilon 6 1 over G6 Here I know the engineering stress strain equation, the general form, and we wrote down the matrix that was the general matrix. This is now the, let's write it here, the engineering stress strain equations, general form. And from this, we wrote down the general matrix and the compliance matrix for the isotropic case, the orthotropic case, and for the other cases. You know, some of these terms vanishes because they are zero, depending on the case. Take for example, you know, we have the orthotropic case once more here. T-H-O-T-R-O-P-I, the orthotropic case. And in material principal axis, there is no coupling between the extension and the stray, and no coupling between the planes or the shear. So that all n and n equal 0. And only the following constants remain in the orthotropic case. E1, V12, V21, V12, E2, G13, and E3, and this is 3 plus 3 plus 3 equals 9. So we have now the engineering stress strain equation, general form, in the linearized equation form. We'll put it in the matrix form, which we said the amazing 5x12 matrix played an attractive power in finding, seeking out these matrices and then seek to analyze the engineering principles and properties of these operations. So this was really developed from our amazing 5x12 matrix. This is a 6x6 square. And we have orthotropic case and isotropic case, and isotropic case, in which some of which the terms vanishes depending on the description below. So we'll yet move on to some more magnetization property of our amazing 5x12 matrix. And this was in our aeronautic and astronautics. We'll establish some in electrical engineering, electrical and electronics engineering. So know that all those analysis, metrical analysis for the solutions to mesh equations, 2x2s, 3x3s, 4x4s, 5x5, higher order and lower order were really founded from the magnetization property of the amazing 5x12 matrix. So as we continue here at the Residence Inn Marriot on West Central Boulevard in Los Angeles, California. We are on the magnetization properties of the amazing 5x12 matrix, or the affinity-like properties, attracting itself to other metrical operations in other engineering fields, medical fields, or whatever fields of interest, because of the exponential amount of matrices that were produced from this process. It sort of have this characteristic magnetization property to attract other matrices and integrate it or bring it into its field. So, in so doing, we have established this aeronautics and astronautic process from it. And we're going to just do some explanation of the terms so that we could have a clearer understanding. This is like working backwards. We first establish our matrix from the magnetization properties, and then we have to go on and explain the parameters and the process. So there is the matrices that was of interest first, and then we have to explain the parameters and whatever so that it makes sense. So let's just take a break, and then we'll come back to do some explanation here. We return to the Residence Inn Marriot in Los Angeles, California, 709 5933 West Central Boulevard, Los Angeles, California. And we're on the amazing 5x12 matrix, and we have sort of deviated a bit from our previous video lectures, and we are on now the magnetization properties or affinity-like properties of this amazing 5x12 matrix and the PDM process. Here's truly Dolphy Gilpin, the president of the PDM process. Amazing 5x12 matrix is here with you once more. And greetings to you over there in Englewood and Fort Lee, the Fort Lee BCCL Library, and the Englewood Library, Engle Street there, a famous library. I just like the design of that, architectural design of that library. And I've done a lot of tweet from BCCL Englewood on these topics, just to highlight what would have come in some more longer sort of lecturing on these topics. The amazing 5x12 matrix and its magnetization property. Note, we spotted the matrix from the Unit 5 Engineering Maths with Professor Lagasse. PAL is his initial, P for Paul, A, Lagasse, and that's spelled PAL in that. initial. And I'm just continuing now to make sense out of all those matrices, and that we have worked from the matrices into the linearized equation. We could have done the linearized equation into the matrices, but because of the magnetization property of the matrices, of the amazing 5x12 matrix, it was first spotted, and then it led to the reverse procedures in these, deriving the linearized equation. But let's just make some more sense out of it. And we see now that there are five, the longitudinal, which was in the tree, the longitudinal or Young's extensional modulus. This was treated from the BCC, then worked with Berlin County Community Library System, and also the Fort Lee, which is also a member of the BCCLS. And this we say now that it relates to the extensional strain in the direction of loading stress. In the direction of the loading. And let's put DIR for direction of the loading. And there were three of these. And then two, this is one, two, we have the Poisson ratio. You'll see it pop up again, Poisson. Poisson ratio. Which relates now extensional strain in the direction, in the loading direction. I put DIR for direction. So the extensional strain in another direction, in another dirt, and that there were three of these as well. Rather, six of these, for the Poisson. Six of these, of which three are independent. Six of these of which three are there, that is a Poisson ratio. For three, we are know the shear modulus, or from the magnetization properties of the amazing 5x12 matrix. The shear modulus which relates now shear strain in the plane of the strain. Loading to that shear stress. Now there were three of these. And four, we have the coefficient of mutual influence. Coefficient of mutual influence is your 18 of these. And five, we have the CHEN. TSO, the Chentsov coefficient, of which there were six of these. And for now, the longitudinal modulus, let's just explain some terms. We have now for 1, E11 or E x of x, or E1 or E of x was the contribution of epsilon 11 to sigma 11. This will help us to explain the elements of the matrices. So we see a lot of E11, epsilon 11, sigma 11. Okay. 2, we have now E22. This is for the longitudinal modulus, or EY or E2 or EY is now the contribution of epsilon 22 to sigma 22. And 3, we have now, and let's go for this is for the longitudinal modulus, Young modulus. E33 or E22 or E3 or EZ is now the contribution of epsilon 3 to sigma 3. And this is for the longitudinal modulus of Young modulus. So the magnetization property of the amazing 5x12 matrix leads to other processes and operation of interest. I know that in general, E m of n equals to sigma n over epsilon n. And this is now due to sigma mn applied only. We do the same thing for the Poisson ratio and do some explanation. Let's just take a break and we'll come back to the Poisson ratio and explain some of these terms in our magnetization process of the amazing 5x12 matrix